Welcome to this lecture on transition metal organometallic chemistry from principles to applications. Over the last few lectures, we have been discussing an interesting topic which is on CH activation. CH activation is a leading area of interest in organometallic chemistry because it has significant utility in both academic as well as industrial world. An important drawback to this this problem is that this problem is very challenging and not a very simple one, and that arises primarily due to strong CH bonds and also because of large number of CH bond present in several compounds, their ubiquitousness also poses a selectivity problem in CH activation chemistry. So, these bonds are difficult to break and also very difficult to selectively perform the cleavage of these. We have also discussed in the last lecture about various methods or various types of CH bond activation chemistry that has been practiced, and what one comes around is there are both kinds of CH activation possible. One is intermolecular, the other is intramolecular. Of these two types of CH activation that is possible, the intramolecular CH activation is less challenging, whereas intermolecular CH activation is more challenging. To attempt. Now, in our discussion on CH activation in the last lecture, we have started off with looking at intramolecular CH activation reactions. And one example that we looked at was that oxidative addition of a CH bond of an aromatic ring onto a transition metal. And that resulted in a complex, a iridium complex shown here. Where this hydrogen and this carbon has undergone oxidative addition. So, this method involves the CH activation of this aromatic ring across iridium, and as a result the oxygen state of iridium increased, and in the current complex it is iridium 3, whereas it started off from a iridium 1 complex. So, because of this oxidative addition of a CH bond, the iridium 1 center increased its oxidation from iridium 1 to iridium 3. As a result, both coordination number increased by 2 and oxidation state also increases by 2, and this type of reaction that we discussed are called orthometallation or cyclometallation. Orthometallation because the CH bond ortho to the aryl ring gets activated and make a metal carbon bond, and cyclometallation is because there is a cyclic ring structure that is formed that contains a metal carbon bond as a part of the cyclic ring. So, one has to then look at various methods or the mechanism in which this CH activation proceed, whether in case of intermolecular or intramolecular reactions. A careful probe into this CH activation reaction shows that CH activation occurs via a interesting interaction called Agostic interaction. That precedes CH activation during this oxidative addition process. So, that sort of implies that Agostic interaction initiates the CH activation mechanism, or Agostic interaction triggers the CH activation pathway. And what it turns out that in this Agostic interaction the CH bond is weakened considerably, but not cleaved. So, this is a very interesting interaction which weakens the CH bond and not cleave it completely, and hence Agostic interaction is often represented by the following. Implying Agostic interaction. Usually Agostic interaction occurs in electronically as well as coordinatively unsaturated complexes. And what one needs to look at is how does this metal center influences or facilitates the CH bond activation through this weak interaction. Even though the interaction is kind of weak, but it has very significant impact in cleaving a very strong bond. Agostic interaction may be weak in nature, but cleaves a strong CH bond, and that sort of puts or that sort of makes this agostic important interaction very important. And then, so if one were to understand CH activation, one should begin by understanding agostic interaction, and one finds that agostic interaction occurs for complexes which are electronically as well as coordinatively unsaturated. So, this unsaturation is a hallmark of complexes that would show agostic interaction. Let us illustrate this with an example shown here. For this complex, eta 3 C 8 H 13 Fe P OMe 3 whole 3 BF 4. The structure is given here. It has 3 POMe 3 moieties, bound to this 8-membered ring. Now, this is 16 valence electron complex, and what it has is an agostic interaction occurring between the hydrogen at this position. So, one of these hydrogen interacts with the iron center in a agostic fashion, which is M type interaction. Now, the evidence for the existence of this interaction came from X-ray crystallography, as this compound was structurally characterized, and what came out from that is that this CH bond interacts and has considerably elongated, and this distance is, which is hydrogen to iron, is about 188 picometer, and this carbon to hydrogen is about 116 picometer. Now, this interaction of this CH bond with the metal leading to elongation of the CH bond to 116 ppm, whereas free CH bond which is not involved in Agostic interaction that have a distance of about 1110 picometer. So, a free CH bond which does not have Agostic interaction is around 110 picometer, whereas in this complex as it shows CH M Agostic interaction, this bond has increased from 110 picometer to 116 picometer as a result of this Agostic interaction. So, what we see that this kind of Agostic interaction is of a non-classical two electron 3 center bond, and similar to the BH B bonds that we are familiar with, displaying such non-classical 3 center 2 electron bonds. So, the X-ray structure of this compound proved the presence of Agostic interaction. It also showed that as a result of Agostic interaction that the CH bond undergoing the Agostic interaction has increased its length to 116 ppm with respect to, let us say, a CH which does not undergo Agostic interaction, which would have a average bond length of 110 ppm. Not only there was a increased CH bond length, the hydrogen is seen interacting with iron, kind of designated by H dot M. This is a weak interaction and has a distance of about 188 picometer. Now, this structural characterization of this complex thus establishes the fact that 18 CH activation is prevalent in this particular complex and many other complexes for both electronically as well as coordinatively unsaturated metal centers. Now, X-ray is not the only way to ascertain the presence of CH activation. Sometimes in X-ray it is difficult to obtain the data for hydrogen atom, and hence neutral diffraction becomes more useful than X-ray for discerning CH activations. And there are other spectroscopic techniques which will allow us to understand the presence of CH activation. So, hence one can say the presence of CH activation can be established by, let us say, neutron diffraction, to be more precise. Sometimes X-ray diffraction as well, where hydrogen is located. Where Agostic CH bond length is around 113 to 119 picometer, where for free CH this is about 110 picometer. Similarly, proton NMR is a useful method, spectroscopic technique for identifying CH Agostic interactions, and they show upfield shifts in the region from del minus 5 ppm to minus 15 ppm. So, this is really very upfield shielded proton resonance, which can be easily picked up in proton NMR, as most of the other proton resonances they appear from between 0 to 10 ppm. Furthermore, in carbon 13 NMR, the presence of Agostic interaction is also prominent. As mentioned earlier, that Agostic interaction leads to weakening in CH bond, which results in lowering of the coupling constants, and that can be observed in carbon 13 NMR, where 1J CH coupling constant, the reduced coupling constant can be something around 75 to 100 hertz. Similarly, infrared spectroscopy would also take up this Agostic interaction, where it shows CH stretching at lower wave number, energy low wave number, new CH is between 2700 to 2300 centimeter inverse, as opposed to free CH, which is around 3000 centimeter inverse. So, the weakening of CH interaction as a result of the Agostic interaction can be reflected in IR CH stretching, where the free CH stretching that comes at higher energy of about 3000 gets reduced to that of 2700 to 2300 because of the presence of Agostic interaction. The same can be seen in lowering of coupling constant. In carbon 13 NMR and proton NMR showed upfield shifts in the region from minus 5 to minus 15 ppm. As a result of this CH interacting with metal center, the hydrogen in the CH becomes acidic, and it shows increased acidic character. Now, let me summarize the points that we have discussed in this particular lecture. We began by looking at various types of CH activation examples that are known. In the start, we looked at intramolecular CH activation, which was a orthometallation type CH activation, in which a orthohydrogen of aryl ring oxidatively added onto the metal center. We also looked at the mechanism how this CH activation proceeded and found that CH activation initiates with an important interaction, which is Agostic CH-M type interaction. This Agostic CH-M type interaction is a weak one, but it has significant implication, as this results in cleaving of a very strong CH bond. So, even though by itself it is a weak interaction, this Agostic interaction, but it has tremendous implication and significance in terms of being able to cleave a very strong CH bond. We also discussed about the criteria that are required for the existence of Agostic interaction, and what was discussed is that metal complexes have to be electronically as well as coordinatively unsaturated to exhibit Agostic type interaction. The presence of an Agostic interaction in metal complexes can be confirmed by X-ray single crystal diffraction studies, where the complex exhibiting Agostic interaction can be structurally characterized. As mentioned, Agostic interaction weakens a CH bond, but does not cleave it all the way, and this weakening of CH bond is reflected in increase in CH bond length with respect to free CH that is not undergoing Agostic interaction, and we had seen in the particular example that the bond length increased to about 116 picometer as opposed to 110 picometer for non-interacting CH bonds. The weakening of CH bonds can also be picked up in proton NMR spectroscopy, where this proton appears in highly upfield shifted region between minus 5 to minus 15 ppm. The weakening of bond also is reflected in carbon 13 NMR spectroscopy, where a smaller coupling constant is visible, and this coupling constant arises between 75 to 100 hertz, and the same can be picked up in infrared spectroscopy, where this agostically interacting CH appears as a much lower energy at 2700 to 2300 wave numbers, as opposed to the free CH appearing at 3000 centimeter inverse. And because of this increased interaction of CH to metal centered in an Agostic type interaction, the CH becomes increasingly acidic in nature, and this interaction increases the acidity of the CH group. So, with this we sort of looked at the mechanism or mode of action of the CH activation, which originates with an important interaction called Agostic interaction, which we have learned in this lecture and looked at how it manifests in different spectroscopic techniques that allows us to characterize this interaction. We are going to look a bit more detail in the CH activation as well as acoustic interaction, and in various kinds of intermolecular as well as intramolecular CH activation process, what are their implications, how good they are, and how people are utilizing all this interaction in carrying out CH activation followed by CH functionalization in subsequent lecture. So, I look forward to the next lecture that will have this elaborate discussion on CH activation, particularly of intermolecular type, and also their implication in various catalytic processes. So, with this, thank you for being with me in this lecture, and I look forward to being with you in next lecture.